Okay, we're going to talk about the history of the periodic table. So in front of you there, I've just put a modern periodic table, part of it anyway. And we know that elements with similar properties appear in the same group. So for example, there's group 1, hydrogen is usually not put in it, but the alkaline metals, lithium, sodium, potassium. Now we know they're in the same group because they have very similar chemical properties. Why do they have very similar chemical properties? Because they've all got one electron in their outer shell. Likewise with the halogens over here, they've all got 7 electrons in their outer shell, and that's why they've got the same number of electrons which control their outer shell, which controls their chemical properties. The modern periodic table, of course, is placed in order of increasing atomic number, which is the number of protons. So hydrogen is 1, helium is 2, lithium is 3, beryllium 4, so on. Now, the first attempt at classifying all of the elements into some kind of periodic table happened about 1865. Now, in 1865, they didn't know anything about subatomic particles. They didn't have no notion of the idea of electrons in shells or so forth. But what they did realize was that there were groups of elements, for example, like lithium, sodium, potassium, which were so similar to each other, but so different to all the other elements, that there must be some underlying reason for that. And we, of course, now know that it's to do with electrons in the outer shell, but they didn't know that then. And it was a long time after the first periodic table was constructed that we realized about electrons. So let's look at the first attempt. This was by Newlands. It's called Newlands' law of octaves. But what Newlands did, he was a British scientist, is he placed the elements in order of increasing atomic weight. Now, they didn't know anything about protons, so he couldn't put them in proton order, but by doing some pretty clever experiments, they could compare the size of one atom, the mass of one atom, to another. So they had an idea of the relative weight. Okay, so he put them in order of increasing atomic weight, and on every 7th element, so when he got up to fluorine there, he started a new line. And then when he got to the next 8th element, he started a new line again with chlorine. And when he did that, he found that he got certain elements which are very similar to each other to appear in the same column. He had no idea why that was so. So, for example, lithium, sodium, potassium, the alkaline metals, they all appear in the same column. You probably recognize this one next to it here. This is the group. They're the group 2 metals. So the idea wasn't met very enthusiastically, because at that time there were probably about 80 elements discovered, and now we have about 100, and every year new elements were being discovered. And what people realized was that if you discovered a new element somewhere, like there isn't an element there, everything after that element is going to mess up the position of every other element, and so the whole system is going to break down. And they said, right, it's only a matter of time before new elements are discovered and the whole thing is going to go. Okay, also people said that they didn't know anything about electronic structure, obviously, that why should there be any pattern, underlying pattern? No one realized why there should be. The next improvement on that came fairly shortly after, and right here, this is Mendeleev's periodic table, this one here. It's a Russian scientist, and he came up with this in, I think, 1869, so not long after John Newlands. But the big improvement he made was, you can see these asterisks like that one there. He left gaps for elements that hadn't been discovered. So he did what Newlands did. He placed all the elements in order of increasing atomic weight. And when every now and again he'd start a new line whenever he felt like it, so that elements with similar chemical properties would appear in the same column. So you can see there he's got, if the alkaline metals, mostly in that column. And he's got the high halogens, the group 7, which are obviously very similar to each other, mostly in that column. As I say, the big improvement event was he left gaps like that one there. And those gaps were for where he thought there was a missing element that hadn't been discovered yet. Now, so let's see why he would have left that gap. Well, let's have a look. If he hadn't have left these two gaps here, then we can see that bromine, which should go in with fluorine and chlorine in group 7, would have ended up in group 5, where it doesn't really belong. So that was his thinking for doing that, for leaving these gaps. People were a bit more enthusiastic about that because it seemed like if there's elements were discovered in the future, it shouldn't be too bad. Now, what made people really think there was something in his scheme was, I think 2 years after publishing this, new elements were discovered to fill those gaps. And I think the two that were discovered very shortly afterwards, a couple of years afterwards, see there's that one there and that one there. So it's after zinc and before arsenic. So if we look on our modern periodic table, there we've got zinc, there we've got arsenic. So the two missing elements are those two there, gallium and germanium. And they were discovered. So upon that, gallium and germanium. Now, what made it easier to find those missing elements is because people knew what they were looking for. In the case of gallium, they knew it must be similar to aluminium. And when, obviously, if you're looking for something, it's a lot easier to find it if you know what it is you're looking for. Same with germanium. And you can probably see there that this one, I'll do it in a different color. This one is between calcium and titanium. And that was found fairly shortly afterwards between calcium and titanium. You can see it's scandium there, which was missing. And then this last one here, we can see here, now this wasn't discovered till I think 1945 during the atom bomb project. You can see it's this one, technetium. And you can see technetium has got a square bracket round its around it there because I think technetium, it's number 43. Technetium was not is a not naturally occurring element. It only occurs in nuclear reactors, and then during the atom bomb project in the Second World War, technetium was made as a result of that. And so that kind of, by that point, Mendeleev's periodic table had been completely accepted anyway. One other interesting thing that Mendeleev did, and I'll show you, sorry, I just rubbed that out, is if you can see iodine and tellurium, you can see here these two elements, iodine, right. Now iodine, if you look in your periodic table, which I'll just show you here, I'll just scroll that up there, you can see that iodine is actually lighter than tellurium. And Mendeleev knew that iodine was lighter, but he still put iodine where it went. He really should have swapped those two around. But he said, the reason he did that was because he could see that iodine obviously belonged to this group 7 because he had fluorine and chlorine. It didn't belong to group 6, and tellurium didn't belong to group 7. He didn't know the reason for that, but if we look, here, it's interesting that if you put them in proton number, which we do in the modern periodic table, tellurium does come in group 6 and iodine comes in group 7. Of course, he didn't know anything about proton number, and it just so happens that tellurium is a bit heavier than iodine, which is quite unusual. If you look at the rest of the periodic table, you look at the order of you put the elements in order of atomic mass or proton number, the order is the same, except for a couple of exceptions here with Te and I. They're an exception. And I'll show you one more exception. Is this one here with more familiar elements to us. We've got argon, which has got a mass of 40 and atomic number 18, and potassium, which weighs less. It's only 39. Now Mendeleev didn't notice that mismatch because in 1869 none of the noble gases had been discovered. They were all unknown. And interestingly, actually, argon was the first one to be discovered here, about 1902. And people were not terribly happy about argon being discovered because, of course, that would have, if you stick another element in there, that's going to mess up the entire periodic table. And very quickly, scientists realized that you wouldn't have to mess up the periodic table if you discovered a new element at the end of every period. So there's a new element there and there. And as a result of that, all the noble gases were all discovered within a couple of years of each other. There's this clue that there must be a new family of elements there. Okay, so when you're answering questions on this, there's a couple of things to remember, is that both Newlands and Mendeleev put the elements in order of atomic weight. They could only do atomic weight. They couldn't do atomic number because they didn't know about protons then. And Mendeleev and Newlands, they knew nothing about electrons. So this whole reason why why should you find similar elements in the same column? It happened, but they had absolutely no reason, no knowledge of what caused it. We do. We know it's to do with the electron configuration.